you have to have that with a fair amount of consistency, right? And that's what we're going for. And then so if the length of your line is too long, and like I say, your voltage, falls below that, then what we have to do is side up in the wiring. So if I was going to run, I don't know, we could even go something crazy like we got the big ones like the 4 aughts and stuff, and that's the one with the where you have like a 4 with a fraction sign and then like a 0. That'd be like 4 aught and 1 aught, 2 aught, and so on. That's when you get the really large wiring, and that definitely all of that stuff is multi-stranded. There'd be absolutely no way in that size that you could have a solid core. And even with the multi-strand, it's some pretty stiff stuff. It's pretty big gauge. It doesn't maneuver well, but yeah, figuring that out and then figuring out the minimum lighting branch circuit stuff on how we have to do that. And I remember you always got to round up on that as well. And if you have any, I'm serious. If you guys have any trouble with any of this stuff, reach out to me. I mean, you can text me. Hell, I don't always answer my phone if you call me. If I don't recognize the number, I get too many telemarketer calls, so I tend not to answer it. But if you leave me a voicemail, I'll call you back. But otherwise, I always answer my texts. I'll always answer emails. I mean, if we had to, we could even go on something like this thing, or even Skype or Google Meets or whatever, and or you can even do it on with the phone with the what the hell do you call it, like that FaceTime, not FaceTime. I don't even know what the hell it but where you can do the video thing, and I can even because I can even set that up and without problems. If I get my paper and whatnot, I just focus the camera on the paper and show you how to work out a calculation if you need to, that kind of thing. Because the cool thing is usually at school with the lab, I always had the whiteboard, and so I could always draw, how we're doing the calculations and that kind of thing. I mean, with the voltage drop, you guys know, right, the K value, and so typically copper. So they have a K value for copper. They got a K value for aluminum. And the homeworks, and quiz, that chapter 3 and 4 quiz now. And also, like I say, if you do have, like, if you got a crazy schedule or something like that, you just overdid it or whatnot, and you need any kind of an extension on time, you got to let me know. Otherwise, I try to give enough time. I know not always does that work out, but so if you do need more time or you want to, an extension or something on any of the homeworks or whatnot, then get a hold of me and we can do that too. And I mean, nothing is set like in stone. I'm at home, so it's like I definitely have free reign as far as like being able to get it in. Now, when we were meeting in labs, it was a little trickier for me. So then I wanted more due dates and whatnot. But with this stay-at-home thing, I got more access to the computer on a regular basis. So so it's not as much of a problem that way. And the way I got these homework set up for this class, I have to. You don't get a final grade for most of them. I usually have to go through them. There's a lot of essay kind of questions, so those always require like a manual grade. And then and also on the one homework, were you guys having trouble? See, I don't know why, but if you were having trouble with that multiple choice one, the A, B, C, D, E, F thing, I know some people have had trouble with that in the past where it doesn't take the answers in right or something. And you gotta let me know that too, and then I'll go ahead and offset the points on the homework for that. But today, today I want to kind of talk to you guys about chapter 28. Let's see if I can find it here. That'll come up pretty good for you all.
Yeah.
Yeah.
All right. So chapter 28 deals with what we like to call overcurrent protection, okay? And what does that mean? It's fuses and circuit breakers. Now, thing with these things, you got to remember, you know, they are required on every feeder line, and you'd have to have them for residential services. Any branch circuits have to have circuit breakers or fuses. Now, in the old days, right, they used to have these, that's too bad too. I actually had some of those in the lab, but they had the old, and this is how it was when I grew up too, they had the old screw-in fuses. And, you know, they match it up where, you know, each branch circuit is rated, so you have the corresponding thing. Now, back then, though, with those screw-on fuses, I don't even know why these were allowed to be sold, but they had every fuse size was a different bore, right? So a different diameter. So a 15 was a certain diameter, so you couldn't mix and match or, you know, by accident put on the wrong one. But the weirdest thing is they had like these overthread adapters, right, where you could screw. So let's say for the 15, it would screw into the 15, and then you could put like a 20 amp fuse in there, right? Of course, if it was originally rated for 15, and now all of a sudden you're putting a 20 in there because you're just a homeowner and you don't know what the hell you're doing. Yeah, you've just created a fire hazard, and that's why I've never understood why they allowed those to be sold. So, and then all the new services, thank God, we have circuit breakers usually. Now, in some of the like sub panels, you know, for the disconnects and whatnot, for like some furnaces or some AC things or things outside, they'll have a little sub panel, and you might fuses in there, and they'll be rated as well. I mean, it matches the line. You can't go like if you had a circuit breaker for like 30 amps, you're not gonna be putting 40 amp fuses down the line for it, that would just be silly. But it happens. People do crazy stuff, but typical deal. So a little diagram right here. You see you got the two switch points before, right? So if we look at it, there's our coil, the little squiggly line thing going on there, where we have our 240 volt source, right? So two lines of 120 apiece going down. Your first disconnect, probably the circuit breakers there, and then going into the fuse and bringing back and around. And this is just a straight Ohm's law deal. If you look at the formula on the very bottom, where the I is the current, so I through the circuit is equal to E over R. So in this case, we only have a 24 ohms as a load, so that would be the R, and then the E in this case is 240, right? Now notice they have a couple of little additions in there besides the 24, right? If you look at that sub note, it says the conductors that are rated at 15 amp, you do have conductor resistance. Now, typically, you know, wire and stuff like that is usually a pretty, and you can even see there, right, 0.015, you know, it's a pretty low resistance rating, but there is a certain amount of resistance to it. So you plug it all together, right, put in your formula and come out how much current do you have running through this circuit. Well, you have 9.987 amps. Yeah, crazy number, but that's just how you would go through, right? And of course, you can see the conductor's rated 15 amps, so you have an ampacity, and even the fuse, right? You have the ampacity to deliver 15, but our normal operating thing would be 9.987, and these things will trip until they get 15 amps going through there. Now, what happens here when you get an overloaded circuit? It's like, how does this work? And the thing to think about, right, it's an overload. And that means that the current has to spike, and it has to spike for a little bit of time for these things to work, okay? Because when you first turn things on, there's like a spike, you know, as a current pull, like when you turn a motor on or something. And it'll jump up and over, but it settles down really quick. So usually these fuses and circuit breakers, they're rated for, they got a little bit of a time, you know, a couple in seconds, of course, but there's a little bit of trip time to them. And if you take a cutaway of what it looks like inside, it's a little coil deal. So yeah, it would take it a little bit of time, and then it reaches that overcurrent, and then it would trip it, or it would blow the fuse. Some cases, fuse just has a filament inside of it, and the filament basically will just burn away. Some are more solid core. It depends on the rating of the fuse. But when you get an overload, right, that's a condition where the current flowing is more than the circuit or the equipment is designed to safely handle. So the reason they put it in there is it's fire protection, right? So if you're driving to a motor or something like that, you don't want to, you know, you'd much rather blow the fuse, which is cheap, than blow the damn motor, which can be kind of pricey. But so yeah, in this case, let's say you know, if we do our calculations to this thing, we can see that if something kind of short happened here, okay, notice what our resistance on the end over there did. You know, let me go back here real quick. See, normal load is 24, but somehow it got shorted out in the parallel here, which drove it up, and then you see it's now no longer 24 ohms, now it's at 12 ohms. So your current just took a big spike because of something happened at the load, and it went up to 19 point, almost 20 amps. And of course the circuit, you know, is only designed for 15. So if it stays at that 20, you're gonna blow those fuses. So now when you get a short circuit, this is an interesting little thing, and that's usually when you get some kind of a bare wiring making contact with some other type of metal, right, where it's bleeding up or something like that. What could happen in the case of a short circuit, you know, resistance goes down. Yeah, it'd be like next to nothing. And if you do the calculations, of course, it would seem like your current would fall, but basically, you're just basically allowing the current to shunt or go around the given load in this case. So that's why it appears like, oh, now my current's way too low. And it does happen. So when you get that type of short like that, notice your circuit breaker might not trip here, right? Because now you're only at 7.7 amps, and normally you're at 15. And that's when we get into something like this. So for that kind of situation, you'd have to have something that can sense that and be a little smarter than the average circuit breaker or fuse. Because a circuit breaker and fuse are what they call like a passive device. There's nothing really in there. It's all basically mechanics, right? There's it's just a reaction, like in a case of a fuse where you get the filament that'll burn out if the current becomes too much for that filament. And a circuit breaker, it has that little coil inside, and it just reacts to something, right? But when we get into something like a ground fault, in the case where we need it to sense that trip right away, because otherwise we could have a fire hazard going on in this case. And that's how we get into, well, we'll get into ground fault connectors, interrupts in a little bit here, but that is setting up that condition. You get a ground fault where you get a break in the line or some kind of short, that kind of type of thing. But this could happen. There's different things that can cause a situation like this. You know, somebody drove a nail through the wall. You could even have critters. I had a on my actually in this house too, on my AC unit outside, right? One year the thing, my wife comes in and she's like, the circuit breaker for the air conditioner's tripped. And I was like, really? And I go out there and I popped it and it immediately went off. And I was like, huh. So I go out, you know, I'm checking out the condenser unit and stuff, and everything looks fine from the outside. So I took apart the little service panel feeding into the unit, right? Because everything from the outside, there was nothing, you know, I thought maybe some kind of branch hit it or something, but everything looked good. But I opened it up and, you know, over the winter, mice had gotten into the service panel here, and there was literally like a cake of moss inside of this thing, and they had even chewed the insulation away from the wiring, so that way it was making like an instant short, and that's, you know, circuit breaker instantly trips. But I had to end up rewiring that whole stupid thing from the fuse panel because they had stripped the wiring back so far. Basically, the whole wiring inside of that service panel was literally stripped all the way. I was just bare wires up to the connector. But yeah, you get weird situations that can cause a ground fault like this. And then you get something where you get an open circuit where it's just a complete break in the line, and nothing happens. Current has to have a path to follow, and if you get an open circuit, you will get zero current in the return. There's just nothing happening. And of course, you know, you won't trip your fuse, you won't trip your circuit breaker or anything like that. It'll just be I'll tell you what, this problem here is more common than you think. You get this open circuit caused by different things, but that'll be one of your biggest troubleshooting problems that you ever run into is this one right here. If you end up working in like a factory or warehouse or something like that, things like forklifts and those power PE things that people can crash them into conduit and whatnot, and then cause this type of situation. Anyway, so there's what I was talking about earlier. These are the plug style fuses. Yeah, notice the screw size is different on each one, so it's got a different diameter depending on the amp rating that it has. Believe it or not, these are, in some houses, these are still existent. They haven't changed anything, you know, and it's a grandfather clause, so if you don't have anything changed, you know, it's still allowed to be. But you could still buy these bus fuses. Different hardware stores and whatnot still carry these. I mean, they're not as big of a demand as like when I was a kid, but they're still out there. So now, what are we looking at? So they call them Type S fuses, and it's in NEC because they're still being used, right? You can look up Article 240.52 and see why they call them a Type S. And the reason being, see, and this is another one of those show and tell things that I could have passing it around, is the way the filament is on the inside is literally shaped in sort of like an S shape, if you will. Anyway, silly little trivia things. But they have them different ratings. Usually, yeah, you get a 15, 20s, and 30s that you pretty much had back in the day. Usual service that they had for these, your service entrance was 60 amp service back when. You didn't have as many appliances as you do these days, right? Back then it was the little refrigerators and stuff like that. Most people didn't even have a washer and dryer in the house and stuff like that. You had maybe one TV in the house and possibly, you know, or a radio. But yep, and there is a wonderful, wonderful little thing. They made adapters for these. And so you could screw it into the fuse panel and then go up to the next size and use a different size. So like a 15 to a 20, 20 to a 30 if you wanted. But like I say, a lot of people never even change the corresponding wiring, so those got to be a problem. Now, then we will take a look at cartridge fuses. Now these are very widely used, and they come in different flavors. Um, a lot of them are in like little sockets, if you will, where they're pressed fit in with spring clips. And then if you look down in the picture here from Galco, the biggest size over there, they do have a screw-in style, and it's generally, and you will run into those if you get out in like an industrial setting and stuff like that. You'll run into those on certain circuit panels. They'll have them where they got them cranked down, and they're in like the 480 lines and whatnot. They typically use those style fuses where they're clamped down, no spring socket or anything like that. You want a good secure fastening. Although the spring is generally tends to be fairly durable, you usually have to slightly pry it apart to get these things out. Typically, they're held in place fairly well. And usually when they go, they'll that middle filament part generally you'll see scorching, if not a complete melt away. They'll get pretty hot, and the filament inside, depending on what style it is and whatnot, but that'll be burnt up, and then yeah, you'll have a charred look to it, that kind of thing. And these days, most homes have this circuit breakers. And like I say, it's a passive type element. It's a thermomagnetic circuit inside of the circuit breaker, fairly simple. And the current, like I say, the current has to be on for a couple of seconds to cause the circuitry to actually expand and then make the breaker trip. Otherwise, if it's just like instantaneous, you'll start to get a slight swelling to it. But then if it settles down, it'll reduce back down to size. But over a couple of seconds, what it'll do is it literally forces the coil to expand out, and that's what causes the breaker to trip. And you can look it up in the NEC, Articles 240, right? And then you look at the subsection 80 and 86, they'll give you the requirements for what kind of circuit breaker styles you can use. Very typically, it's the thermomagnetics or the temperature sensitive types, right? So if it gets too hot or if the current gets too much for it, and it just trips. So an NEC permits 100% loading on an overcurrent device only if it's listed. So you would actually have to check and make sure that you are matched. Because if it's not listed correctly for that, what'll happen is you could literally be using something where the load would be up at 100% and you'd be driving, but it wouldn't trip the circuit breaker properly, in which case it would turn on. Next thing you know, you have fire, and that's the way that goes. And we don't want that. So you have to make sure that you're properly protected for your feeder lines, your branch circuits, if you will. And if we specify a UL, that's Underwriters Laboratory, which is a nationally recognized testing laboratory, the NRTLs. There are a couple of other ones out there, but UL probably has the biggest audience, if you will, where you'll see them on a majority of equipment. And that's how you can tell typically, right? If you get equipment and you literally, I don't know, and I'm not trying to knock China, but let's say you get some cheap Chinese knockoff crap, check it. If you don't see like an Underwriters Laboratory stamp on it or some other kind of lab stamp, and it's just completely blank, and all you see is maybe the manufacturer's seal on it or something, yeah, there's something, I don't know if I would necessarily trust it. I mean, that could definitely be cause for a problem. So, yeah, in most cases, you never really want to go for anything where you get, 100% loading. Usually you get to a certain point to that and have it trip at that point. So we use two styles typically. You'll see in your panel. You'll get the single, right? And that's the one on the right-hand side where it's just a 120. You have one line attached to it. And then you get the duals, right, which are for 240-volt circuits. And these will generally be set, but they do come in like 20 amp sizes as well. Generally, you'll see them in the higher ranges, the 30s, the 50s, the 70s, that type of thing. And you'll have two lines coming into that, so two hots. Oh my God, my dog is crazy. Sorry. So, and then you can look up, they do have a rating, right, where like an NEC 110, and this is the very beginning of the book. We didn't even read this right. It's equipment intended to interrupt current at fault levels, and it shall have an interrupt rating not less than the nominal circuit voltage and the current that is available at the line terminals of the equipment. See, and it's a thing with all this. It's always like lawyer speak, right? Legal speak, if you will. So really, it's like, okay, so what the hell does that mean? So you basically, you have to figure, it's like, so what is my ampacity for this given line, right? And what is my trip point, if you will? And nothing, you never ever really want anything to run like full bore, you know, at the full maximum. It's got to be able to have a certain settling point, like if you will, and you know, when it'll trip. And that's really all it's looking at. So service equipment, depending on the ratings that you have on it, could be series rated, right? And that'll be on the what kind of panel board you're allowed to use. And then fully rated, everything has the interrupt rating listed. The series rated systems are less costly. The fully rated one, of course, is ready for just about everything. And really, you have to apply it to your situation. It would depend on what kind of home and what kind of home wiring you're going to be having, what kind of appliances that are going to be run through the house, and that kind of thing. So if we look at this, and this is a typical example, right? If we look at the first one, that's our, well, the double coils, that's their basically your transformer on the line. And then coming in at the first fuse marking is your service disconnect. So that would be the main breaker on your panel. Hey, stop it. And then each other, the corresponding ones down below, that's each of your branch circuits that feed out. So it's just like a simplified drawing of your panel. So fully rated system, you know, everything is tested, listed, marketed. So you don't have any qualms, you know, everything's got a label on it, underwriters or whatnot. Usually though, when you're going for that kind of style of system, like see in the bottom line here, you'll generally only find that in like a commercials and industrial settings, right? Because they're the ones where they have the heavier equipment and that type of thing where they're using things like that. So you have to go for, you know, the fully rated systems. And like I say, that'll be generally a little more costly. But otherwise you wouldn't have, you would just use like a series rated for most residences, unless the residence had a lot of toys in it, you know, saunas and that kind of thing, you might end up going. But usually the series rated ones are typical for a home, because you're never going to get that kind of like current draw, really, if you will. I mean, if you look at this thing, right, what are our interrupts ratings? This one, you have fault current for 20,000 amps, okay? You're never going to have that. Hold on one second, right, guys? I'm sorry, I had a little altercation with my dogs there for a second. Anyway, see if I can get this back in here now. I actually didn't have that much more to go either. So generally, when you look at this, I'm so sorry, guys. I really didn't mean that. There we go. Everybody able to see it okay and everything?
Yep. Everything's still up.
So slides were coming through earlier too, right? We weren't having any trouble with that, I hope. God forbid.
No.
All right. So now, so yeah, series rated and fully rated are pretty much your two styles. And like I say, the fully rateds are usually what you'll get in, commercial and industrial type settings. Very rare you'll have it in a like a home, but you gotta take that with a grain of salt. Some homes it depends, right? But typically series rated for residences, that's pretty much the way to go. Then they look at something they call short circuit current, and the ratings involved and that type of thing, because it all goes back to what's going to happen, at the transformer, because the transformer isn't protected. Really, what's coming in as far as protection goes, it's what's coming into your house. And that's how you have to look at that. And generally for that, you'll notice they have a rating there, the KVA. Now, K is the thousands, and VA is, of course, instead of using watts, we use VA as volt amps, the ampacity for the overall circuit. And then we'd look at the impedance values of the transformer itself and what's involved there. And that's, and it does happen. Like I say, you'll get situations and that transformer will, it'll blow, and it makes a hell of a noise, because there isn't much in the way of resistance on those things. They're just giant coils, right? Immersed in, like I say, this big pool of oil inside of those cans. So when they do short out like that, it'll go pretty big. But in any case, so when you look at like your how would you calculate short circuit current? But so that's like looking at it overall. It's like you have to take, just like with anything with this, what's my weakest link in this whole situation? Well, in this case, it is the transformer. So it has such a very, very low resistance value. Again, we're only really using, this is like a juggling around of like Ohm's law, right? So what we look at is a single phase transformer, and this is typical for residents. Now, if you get into a commercial or industrial setting, it might be a little different depending, and you'd have to take that and then use a different formula for that. Actually, if we're dealing with like a three-phase style system, the formula will be similar. We just have to take into account all three phases. In this case, we're just looking at a single phase. Excuse me. So with that in mind, so basically what we do is, okay, so your transformer is rated at 100 kVA at the 120/240, right? So you have an impedance like 1%, which is pretty low. I mean, it's very, very minimal. And so to find what your short circuit current would be for this thing, you basically would set your I, which is standing for current, right, equaling your KVA multiplied by 1,000. And that's figuring out what the resistance value is going to be of this thing divided by the voltage. So in this case, we have our maximum rating is 240 volts, usually going into the home because you have the two lines. But still remember, this is only a single phase system, but that's what you would use. So then what you would come out in this case, so we have to take the rating. So in this case, we have 100. So 100 times 1,000 divided by 240, and they figure out the 416 amp full load current. So how would you do that? Well, in some cases, yeah, it'd be 4 100 amp services where you would literally have 4 different panels, right? 1, 2, 3, 4, each one rated at 100, or 2 200 amp services. And believe it or not, sometimes some of the homes these days actually do call for a 400 amp service, in which case you would be doing a dual panel, or possibly the 4 panel, or some kind of combination thereof, you know what I mean? But in any case, so how do we calculate it? And this just gives you like the steps and how to go through it. So you figure, and really it comes back to what the rating on the transformer is going to be. So what we have is the multiplier for your transformer impedance for 1%. And like I say, it is going to be really, really low. So we look at it 100, divided by the percentage of impedance. So in this case, as an example, they use an impedance of 1. So 100 divided by 1, of course, is 100. So then you just go through and multiply out, where your current times your multiplier, right? So you figure the 100 times the 416, and that means you have 41,600 amps for line-to-line short circuit current. And that's just like something crazy, but it's very, it could happen. That's with the transformer line and whatnot. But it's actually a pretty simple calculation, if you will. And that's really all you have to do. It'd be check, okay. And you wouldn't even have to check the nameplate on the transformer. That'd be something like information you can get from Ameren or the ComEd lineman, that kind of thing. And they'd be able to give you that information usually. And that's just something you'd use to basically, when you're doing your calculations for the residents, for, like sizing what my service entrance is going to be, that type of thing. This would be one of the calculations you would need to be using as well. And these are some typical like commercial or industrial panels, if you will, pretty standard. These days, I would generally go with the bigger style if I was putting in something new, give yourself a little room to grow if you need to. You got load centers, resident for residences. These are smaller. But again, it's still, depending on, you'd have to figure how many branch circuits and things like that you have. God, my dogs, I'm so sorry. But yeah, you have to make sure these things are stamped. When you look in there and you don't see any kind of like listing or labels or any kind of numbers or something like that, I would look at it kind of funny and be questioning how well built this thing is, and if I'm going to be able to actually use it or not. Shh. Oh my God. And this is really it. Chapter 28, this is all they're looking at. It's something that we do have to look at, because when we're sizing up the panel, when we're doing our service entrance and that kind of thing, this is one of the main considerations to go through. What kind of overcurrent protection am I going to need for this home, and make sure I'm properly rated, properly sized. I'm using the right kind of equipment on the install and that type of thing. But generally, I mean, it's not usually that bad to go through. Again, you just look at what your overall pool is going to be with this thing. How the transformers rated, and you just got to make sure everything's protected. Again, it's always about fire, right? That's the NEC's main thing, is fire prevention, basically keeping people from accidentally killing themselves. But that's it with chapter 28. Really, it's a pretty easy chapter, and I got the homework for it. I also had, hold on here, let me pull up if I can find it. Oh, stop sharing that. Let me find this real quick here. So if we look. Yeah, so for today, yeah, we have chapter 28, but I also am pointing your first uglies quiz. So this quiz, all the answers are basically totally out of the uglies book. You need to find that if you go through it and find it. What else do we have? I'm also assigning, for our next meeting and whatnot, go through and read chapter 5, and we have the chapter 5 homework. I'm also giving you the chapter 28 homework. I know it's a lot, but chapter 28 is due sooner and the chapter 5 is due later. And the other part we won't be able to do, because this is basically one of the things I had you do is go through and start building your own service panels and getting it populated and whatnot. But that we won't be doing for lab or not whatnot. So yeah, instead you're going to get chapter 28. That's due sooner. Your uglies quiz, I think, is due by Wednesday. And then chapter 5 is, I think, by the end of the week or Monday. I'd have to hold on here. Look real quick. Yeah, because 29s was due today. Yeah, your uglies quiz is due by Thursday. Yeah, 28 homework by Friday, and chapter 5 homework on Monday. Yeah, keep you busy. No. But yeah, and after these three, because towards the end of the book here, right? We go 1, 2, 3 with those 3 chapters dealing with basically all around like service entrance and service entrance calculations, that type of thing. And then we jump back into the normal flow. We left off with chapter 4, so now we're going to jump on to chapter 5 and go with it from there. And that's pretty much it for today I got for you guys. Did you have any questions, or you guys needed me to go over anything?
I was like, on the chapter 29 homework, I got since it's past this dude. Yeah, I was kind of confused how on doing it, because I was going to steps and referring to I did trouble finding those tables that I was referring to.
Yeah, that's the appendices, right?
Yeah, but the appendices says I refer to table 220.55.
Doesn't have all the tables in it. I don't know if it'll all come up for me or not.
This is on step 6, or step 7 for electric range, wall mount ovens, counter, which we had electric range. It says use table 220.55.
Well, let me see if I can get this pulled up here, Jerry. Oh, stop. Oh, this thing is taking forever to load.
I think you're Googling. I think you're looking at the wrong tables. I said it's two.
There's a lot of material in this appendix. I just wanted to see if I had all of it in there or not. Oh, this thing is gigantic. It'll eventually load. What is
But the step is on step 744.
Say it again?
The step I'm talking about is on page 744.
You said 744? All right, and which one was it calling for?
Electric rooms. Right at the bottom of the page.
Oh, electric range, wall-mounted ovens, counter-mounted units, table 220.55, and that's not through the. Let me think.
Like I looked through like the index too, since that's the index of the bottom, and when it referred to the table, in the book, it was only referring to when it's like table references. It doesn't go it.
Yeah. I think here. Huh. Yeah, we would have to have that directly out of the NEC, wouldn't we? Crap. Well.
It's like all these steps referred to this is referred to an article or a table.
Oh well, yeah. I mean, all of it is right. I'm trying to remember.
Like those tables aren't really clear spot.
Trying to think. I could pull this now. Yeah, let me see if I can get a hold of the tables themselves. I'll try to post them. You know where the textbook is at. Otherwise, we might have to skip that there question, huh? All right. Yeah, let me see if I can't get the those tables posted up, and if not, we'll have to bypass that question. And that's in chapter 28, you said?
Chapter 29.
29. Okay.
29 homework that was due before class started.
Right. Oh, all right. Yeah. All right. Well, yeah. I guess we'll have to let that one go. But I'll go through I'll go through that homework and make sure for the reference for that one. I'm sorry. Yeah. See, normally, like I say, I had the NEC books right at school, and so I usually could just, you refer to it right then and there and get what tables we needed. But all right, my bad. I'm sorry. This is my first time teaching this class online, so I haven't gone through everything, if you will.
I imagine this class is very much a pain to teach online, and you've heard everything when everything is pretty much meant to be in person.
Yeah. But all right, sir. No, I guess we'll bypass that question for now, I guess. But I'll see if I can't. I might be able to actually pull that table up. Probably, I don't know. But yeah, I'll see if I can't find that table. We might need to refer to it later when you're doing your service entrance calculations and stuff. But I'm sorry. You guys have any other questions? Or we're doing okay so far? Or? Nothing?
Nope, nothing at the moment.
All right. Well, like I say, I really, if anything's stumping you, or you're having a hard time with anything, definitely get a hold of me. And we can work out a way to definitely get in touch and whatnot. All right.
All righty.
And I'm going to go beat my dogs. No. They're all being goofy. But all right, guys. Well, then I will see you all on Thursday. But yeah, But yeah, if we run into any of this crap on the homeworks that are like that, where I referred to NEC and stuff, you know, where it definitely had to come out of the book, just let me know, and we'll kill that question or bypass it or whatever we need to do. But oh, sorry. All right, gentlemen. Then I guess I will see you guys on Thursday, and then like I say, any questions, just hit me up. All right.
All right.